Look closely at Earth, and almost everything around us is built from ancient ingredients. Oxygen, silicon, iron, carbon. Earth contains a chemical diversity. The young universe did not begin with. Trace those atoms backward, and Earth's history quickly becomes a story much older than the planet. Before Earth existed, its future material was scattered through the gas and dust surrounding the young sun. Before the sun formed, that material belonged to an interstellar cloud, enriched by earlier generations of stars. Those earlier stars inherited simpler material and somehow returned new chemical ingredients to space. Continue backward far enough, and every star disappears. So do every planet, rock, ocean, and living world. The young cosmos became dominated by hydrogen and helium, with only tiny traces of other light nuclei. There was essentially no primordial carbon, oxygen, silicon, or iron available to build a rocky Earth. The early universe could not build Earth. First, it had to invent a way to manufacture new elements. Our planet was not made from the universe as it began. It was made from what the universe became. Without those later elements, there could be no Earth-like rock, iron core, oceans, or carbon chemistry. Earlier, the universe was so hot that matter existed as an ionized plasma filled with freely scattering light. As the universe expanded, its radiation cooled, and the average density of matter steadily decreased. Eventually, conditions cooled enough for electrons to become bound to nuclei, forming mostly neutral atoms. With far fewer free electrons to scatter them, photons could suddenly travel enormous cosmic distances. That ancient radiation still surrounds us today, stretched by cosmic expansion into the microwave part of the spectrum. The universe was finally transparent, but there were no stars yet to fill that transparency with visible light. Yet the young cosmos was not perfectly uniform. Some regions contained slightly more matter than others. Gravity amplified those tiny differences. Denser regions attracted more matter and became denser still. Dark matter deepened gravitational wells, helping ordinary gas collect into the universe's first growing structures. Inside these early structures, primordial hydrogen and helium gathered, cooled, and began contracting into denser clouds. As gravity compressed the gas, its center grew denser and hotter, storing enormous gravitational energy.
Gravity had transformed darkness into pressure and heat. The universe was now approaching a completely new kind of object.
Eventually, the core became hot enough for hydrogen fusion to begin. The first stars ignited. Inside stellar cores, fusion converts hydrogen into helium, while releasing energy that can support the star. Gravity pulls inward, while pressure from the hot stellar interior resists collapse, creating a long-lived balance. After an immense cosmic darkness, stars began filling parts of the universe with newly generated light. Energetic radiation from early stars also began ionizing the neutral gas surrounding them.
These primordial stars formed from almost metal-free gas, unlike the chemically enriched stars that came later.
A star's mass determines much of its evolution, including how hot its core can eventually become. When core hydrogen becomes depleted, sufficiently massive conditions can eventually allow new stages of nuclear burning. During helium burning, the triple alpha process can produce something but the primordial universe scarcely possessed: carbon. For the first time, stellar interiors were manufacturing substantial quantities of elements that the early cosmos lacked. Much of Earth's oxygen also reflects stellar nuclear processing before the solar system ever existed. Stars had solved part of the universe's problem. They had become factories for entirely new kinds of matter.
Inside a massive star, evolution creates progressively hotter regions where different nuclear reactions become possible.
Helium burning creates carbon, while further reactions can produce oxygen, two elements central to Earth's later chemistry. As successive fuels are depleted, the core can contract and heat enough to unlock still more advanced reactions. In massive stars, still hotter burning stages can build oxygen and progressively heavier nuclei. The later burning stages become dramatically shorter as the massive star approaches the end of its nuclear life. Eventually, nuclear processing builds material concentrated around the tightly bound iron group region. Fusion powers stars when nuclear reactions move matter toward more tightly bound states while releasing energy. But that energetic advantage does not continue forever. The iron group region lies near the peak of nuclear binding. Beyond this region, fusion toward heavier nuclei no longer provides the same source of stellar energy. Yet Earth contains many nuclei heavier than iron. Ordinary energy-producing stellar fusion cannot explain them all. The star has reached a limit. What happens next will change both the star and the chemistry of the universe. For a sufficiently massive star, an iron group core can grow until ordinary pressure support can no longer hold it. When support fails in a sufficiently massive stellar core, gravity can drive a catastrophic collapse. At extraordinary densities, the collapsing core enters a regime where nuclear matter and neutrinos become crucial.
In a successful core collapse supernova, the star's outer layers are blasted outward into surrounding space.
The explosion also creates extreme conditions where additional nuclear reactions can reshape the star's chemical inventory. For the first time, much of the star's manufactured material is dispersed across interstellar space. Each generation could leave surrounding gas more chemically enriched than the material from which it formed. Yet the origin of the heaviest nuclei cannot be reduced to one kind of stellar explosion. In extremely neutron-rich environments, rapid neutron capture can build nuclei far heavier than iron. Some stellar deaths leave neutron stars, city-sized remnants containing extraordinary amounts of neutron-rich matter. When neutron stars merge, neutron-rich ejecta provide conditions capable of producing many heavy R-process nuclei. Gold is one familiar example. But these events can produce a broad family of heavy nuclei. The universe now had far more ingredients for Earth. But those ingredients were scattered across interstellar space. Stellar death enriched space, but most interstellar matter remained hydrogen and helium, mixed with smaller amounts of heavier material. Some heavier elements became locked into microscopic solids, silicates, carbon-rich material, and other interstellar dust. Then gravity repeated its ancient trick. Part of an enriched cloud began collapsing under its own weight. As the cloud contracted, a new star formed near the center, while surrounding material retained angular momentum. Around the young star, leftover gas and dust settled into a rotating protoplanetary disk. Inside the disk, temperature and chemistry determined where different materials could remain solid. Dust grains collided constantly. Some bounced or broke apart. Others adhered and formed larger aggregates. Across time, some solids grew from microscopic dust toward larger aggregates and pebble-sized material. Eventually, concentrations of solids produced planetesimals, large bodies whose gravity could help accelerate further growth. Gravity then drove larger collisions and mergers, assembling planetary embryos from generations of smaller bodies.
For the first time, ancient stellar material was being assembled into entirely new rocky worlds.
Among the worlds assembled around one ordinary star was a planet built from this recycled cosmic history. That young rocky world kept changing. Eventually, recycled cosmic material became the Earth we know. The hydrogen in Earth's water is ancient. Much of it traces back toward the early universe itself. Carbon came later. Stellar helium burning created an element that would become central to Earth's living chemistry. In sufficiently massive stars, advanced burning produces and transforms nuclei such as neon, magnesium, silicon, and others.
Silicon and iron required still more advanced stellar processing, helping make rocky planets physically possible.
Many very heavy nuclei required extreme neutron-rich environments, including events such as neutron-star mergers.
Earth's elements, therefore, have no single birthplace. Their histories span radically different cosmic environments.
Generation after generation, stars formed, transformed matter, returned material to space, and enriched what came next. Eventually, material carrying those different histories met inside the cloud that formed our solar system. Dust became larger bodies became worlds, and cosmic chemistry finally became geology. The rock beneath us is therefore not merely ancient. Its ingredients carry histories older than Earth. Somehow, this chemically simple universe eventually produced a planet containing nearly the entire natural periodic table.